Alright, in this part we are going to walk through what MAML is, how it works in a reinforced learning setup, and how the pieces fit together visually. So what exactly is MAML? It stands for Model Agnostic Meta Learning. And the idea is pretty simple. Instead of training a model from scratch every time we face a new task, we want to learn a starting point, a set of parameters that can be adapted very quickly to different tasks using just a few gradient steps, especially useful when we don't have much data per task. You can think of it as learning to learn. Instead of solving one problem very well, we are training the model so that it becomes good at adapting to any task we might throw at it later. Okay. Now let's break this down with the animation. At the top here, we have got the meta policy initialization. That's the center point marked as theta. That's our initial policy parameters. These are the weights the model starts with before seeing any specific task. Then we have got different tasks laid out, things like forward running, backward running, jumping, climbing, and these are shown as points around the center. Okay, that is done. And the colored lines connecting from the center outward show how theta is being pulled in the direction of different tasks. Each task pulls on theta a little differently. This is what happens during the meta training phase. The goal here is to nudge theta in a way that makes it a better starting point for all tasks. Okay, below that we switch to task specific adaptation, and here's what that means. After we have got theta and we get assigned to a task, let's say backward running, we take a few gradient steps and update theta just for that task. The updated version is called theta prime. Okay, and that new adapted version is what's actually used to perform on that specific task. Okay, and these blue dot lines that you see here, what are they? That's the adaptation path from the general theta toward a specific task point. Okay, so why do we need both phases? Meta policy learning is about building a good foundation. Task-specific adaptation is about fine-tuning it quickly when a task shows up, but both are necessary. Okay, and right under that we have got some sliders, meta learning rate and adaptation learning rate. These control how aggressive the updates are. Okay, you can change. Okay, and meta learning rate, which is labeled beta, determines how fast the main meta policy changes. Okay, and if we set these too high, the model might overfit to just a few tasks. Too low and it will learn too slowly. And adaptation rate is here tells us how fast we adapt to a single task. So you might want this to be higher if you want quicker fine-tuning when facing a new task. Okay, alpha and beta is here. And now let's look at the algorithm steps, which are broken down nicely here. First, we sample a batch of tasks. That just means we pick a few different environments, maybe forward running, maybe backward running, jumping, climbing, each with their own dynamics or reward setup. Second, for each task, we collect pre-adaptation data. This means we run our meta policy data in those environments and record what happens, basically collecting trajectories. Third, we compute task gradients. So using those trajectories, we calculate how the model would need to change if it were to perform better on that task. Then we go on and update the policy for each task, just for that task. These updates give us theta prime, adapted versions of the original policy. Once we have those adapted policies, we collect post-adaptation data, and this shows us how well the adapted versions are doing. Then comes the meta gradient computation. That part looks at how well each adapted version performed and calculates the gradient for the original theta based on that. And finally, we update meta policy so theta gets refined based on how well it helped the model adapt. Okay, you can think of this as let's adjust theta in a direction that makes adaptation work better next time. And let me pause a bit here and walk you through the math on the screen. And here, the first one is how we adapt to task I. It says, take the initial theta and subtract alpha times the gradient of the loss with respect to theta. So basically one step of gradient descent using task I's loss. Next meta update is here. This one says update theta using the average loss across the tasks, but calculated after each task specific adaptation step. That's how we make theta better for the next round. And task distribution is here. There are 4 different tasks here: forward running, backward running, jumping, and climbing. And they are not just randomly assigned. Each one has different dynamics, like different reward functions or environmental behavior. And the algorithm's goal is to train a policy that, when faced with any of these tasks, can adapt quickly. That's why having a good theta matters. And lastly, at the bottom, you will see some notes on what makes MAML useful. First one is rapid adaptation. That's really the core idea. Instead of learning from scratch, we adapt fast using just a few steps. Then there is model agnostic, meaning this approach doesn't care whether the underlying model is a neural network or something else, as long as it can be trained with gradient descent. Task generalization means that we are not overfitting to one specific task. Instead, the model finds shared structure across tasks. And the last one, continual learning, is here, is about the ability to keep improving as new tasks arrive later on, without starting from zero each time. So yes, this is the full loop. We train theta so it can serve as a general purpose, adaptable policy, and we constantly update it based on how well it helps us adapt to new tasks. Thank you for listening.